Hello, welcome back. In this segment, I will show to you how we can do symmetric encryption together with ElGamal encryption. Remember, one of the limitations of ElGamal encryption is that the message must be part of the group. Okay, if you recall, ElGamal encryption, it's made of a few things. We need a group, cyclic group. Order of the cyclic group is, say, Q, and we need a generator, right? And then we need a public key, which we denote it by H, and a private key. So these are the 5 things we need for ElGamal. Okay, these 4 public, right? And this is private. This is private. Okay, for a sender to send a message, he needs to have the message M. The message M must present in the group. Okay, that's a problem. What if the message is not part of the group? It may be a natural language text you are trying to encrypt, and it may not be a group element. So how do we handle that? So there is a nice trick we can do to make this work for ElGamal. What we can do is, this is called the hybrid encryption. We will only do ElGamal just for key exchange, but do the encryption using AES or any other equivalent algorithm. So how do we do that? So remember, H is related to X by this interesting relationship. H is equal to G power X. Okay, all right. So if the sender wants to send a message to the receiver, let's say Alice is here, and Alice wants to send a message to Bob, what she will do is she will first go ahead and generate Y, a random number Y. So Alice will just randomly pick an element Y from ZQ, meaning from 0 through Q minus 1. She randomly picks an element, and she then computes G power Y, okay, in mod P. Okay, I'm going to work only in Z star P group. So whatever group you're working with, you can apply the definition of exponent. And let's say G power Y is C1 as a notation. For encryption, we need an encryption key, right? How do we do that? Alice actually is going to generate the key as follows. This is the key K by just doing a hash of a special hash function I will explain in a moment. The input to the hash function is H power Y. Okay. What is H power Y? H power Y is nothing but G power XY, right? Only Bob knows this. This is Bob's secret. So Bob knows X. So I will put X here, Bob's side. So now this X is already known to Bob. Of course, G, Q, all of these things are known to Bob. Alice only knows G, Q, G, H. Okay, all right. So Alice wants to send a message to Bob. What she will do, she knows the key now. This is the key, right? So she's going to apply whatever algorithm, let's say AES, for example. It need not be AES, but it could be AES. Let's take it as AES. So she's going to apply AES. I'm not writing all the AES IV and all of the other parameters, but imagine AES is called using this key and the message that she has. Okay, they have to agree on the AES in cipher mode and so on, but that's not something I will talk now. This is how Alice will encrypt the message M using the key K. And she's going to get a ciphertext, say C. Okay, what is she going to send it to Bob? Bob is going to receive 2 things. He's going to receive this first C1, which is just G power Y, right? G power Y. And then the ciphertext, say C2. Okay, call it C2 here. So how will Bob recover M from it? So in order for Bob to decrypt the C2, he needs the same key. So how will Bob construct the same key? He has to kind of run this same H function, right? But then he needs to know Y, but he doesn't have Y. Y is only known to Alice. So how will Bob apply? But if you expand H power Y is nothing but G power X Y, which is nothing but G power Y power X, right? Which is nothing but C1 power X. So C1 is coming anyway to Bob. So all Bob is going to do is he's going to take C1 power X, that will be, and then he calls the hash function on this. And now, you know, this is nothing but key K. Once the key is available, he can go ahead and do the AES decryption and recover the message M. Okay, I have not talked about the hash function H. What are the properties H should satisfy? That's an important aspect. I just wanted to tell you how you can do key encapsulation using this little neat trick that I just explained to you and still make use of ElGamal encryption idea. Okay, this scheme is secure as long as the hash function H is chosen properly, and we are only going to assume here CP is secure. Okay, meaning if the attacker modifies let's say the attacker modifies the ciphertext C1, right? Ciphertext C1 is modified, then the key that the Bob is going to derive is a wrong key, so it's very likely not going to reveal M. M will be not decryptable by Bob. So this scheme is CPS secure, meaning nobody's allowed to tamper with the plain text, the ciphertext rather, only observe the ciphertext. Okay. All right. So what about the design of H now? Let's spend some time talking about H design. H itself must be a good function, meaning let's say we are going to use AES in 256-bit mode, so as a key size. So what we need is a hash function H. It's not exactly a hash function in a strict sense, but we can imagine like this. H takes a group element, right? This is the group element that we are working with. It maps to an n-bit uniform string. Okay, n-bit in this case is 256. Suppose our goal is to get a 256-bit AES key. So our H should be mapping the group element to a 256-bit AES key. How do we define such a H? All I did actually is I just made use of HKDF function. Okay, we talked about HKDF. You can look online about HKDF. HKDF is a key derivation function which extracts uniform or close to uniform string, right? We need a uniform key or close to uniform. Otherwise, the attacker will know what are the possible keys that H will map. We don't want that. And HKDF is an interesting hash function in this context. That's the reason I use HKDF. But my main message is to tell you that if there is a hash function H like this, that it's going to map a group element to a uniform string, binary string, which you can use it as a hash function, and of course as a function for obtaining your key K. Then you can apply ElGamal encryption for CPS security in this context. Okay, so that's basically it. So what we have discussed today is that Bob publishes his public key, right? What are the parameters? G, the group G, the order of the group, the generator of the group, and the public key H, which is nothing but G power X, right? And he keeps the X private to himself. X is private. Alice will go ahead and randomly select a number R from randomly select a number Y from ZQ, meaning from 0 through Q minus 1. Alice will compute G power Y, and then Alice will apply the hash function on H power Y because H is public, and use this K as the encryption key and use the regular AES encryption. In this case, the message need not be part of the group. It can be anything. As long as AES is happy, we are good. Now we get a ciphertext C2. So this is the helping text for recovering the key. Okay, Bob can recover the key K because he knows the private key X, and he is going to do C1 power X. What is C1 power X? C1 power X is nothing but G power X, G power Y power X. That means he will be getting exactly the same hash value that was computed by Alice, because H is G power X. So Alice also computed G power X power Y. Okay. So this is basically it, how to derive a key that can be used for encryption using AES and still use the ElGamal idea of encryption using the discrete logarithm problem. Okay. By the way, the actual security depends on the DDH hardness problem, which we talked about earlier. If DDH is assumed to be hard, then this scheme that I just talked about is CPS secure. Okay, the proof is similar to what we proved earlier when we discussed the key exchange for Diffie-Hellman, as well as we talked about CPS security of raw ElGamal. Okay, it's still vulnerable to chosen ciphertext attack because somebody can modify C1 and then they can get that means the key Bob derives will be rubbish. So we will talk about how to make this CC secure later in the next segment. That's all. Thank you very much.